All right, speaking next is Ji Tao, and he's going to discuss architecture preserving provable repair of deep neural networks.
Okay, so deep neural networks have been used in many applications, and they have become the state of the art. Okay, sorry. So deep neural networks have become the state of the art for many applications, like image recognition, where they can be used to identify cat images. DNNs are also used in safety critical applications like aircraft control. However, DNNs can make mistakes. So what do we do if the output of the network is not correct? We want to repair the network. That is, to modify the DNN to correct its behavior. The repair of the DNN should generalize to other similar inputs, and it should be local to not impact unrelated inputs. We also want to repair an infinite set of points represented by a polytope, such that for all input points in the polytope, the behavior of the network is repaired. We refer to this as polytope repair. One way to repair a network is retraining. That is, to train the network with the training data and the new buggy inputs. However, retraining does not guarantee to repair the network, does not support polytope repair, is not efficient, and requires access to the training data that may not be available. Another more efficient approach is fine-tuning. That is, to apply gradient descent on the network with only the new buggy inputs. However, it suffers from similar issues, and it might be less effective. In this talk, we will be focusing on provable repair of deep neural networks. That is, to guarantee that the repaired network satisfies the repair specification. Pardon is the state-of-the-art approach, and it introduces our new architecture called decoupled DNN. Pardon guaranteed to repair the network is local, and it generalizes. However, pardon is not architecture preserving, and its polytope repair is not efficient. Reassure is a more recent approach. It also guarantees to repair the network, and it is also local. However, it is also not architecture preserving and has inefficient polytope repair. Furthermore, it does not generalize, and it introduces a huge overhead to the repaired network. To solve those issues, we propose our architecture preserving provable repair of deep neural networks, or APRN. APRN also guarantees to repair the network, is local, and generalizes. Furthermore, it is architecture preserving and supports efficient polytope repair and scales to large networks and complex properties. Apron is the first that has all those features. And Apron also supports non-piecewise linear activation functions that has linear pieces. Apron is implemented in PyTorch. In this talk, we will restrict to fully connected ReLU networks, but it supports more architectures. Now I will give a brief overview of our pointwise repair approach, using a very simple network and a pointwise repair specification. We will first talk about the semantics of the network. A fully connected ReLU network can be represented by a layered directed graph, where we have weights on the edges and biases on the neurons. The input to a neuron is the weighted sum of the output from the previous layer, then plus the bias. For those double-cycled ReLU neurons, the output is the same as the input if the input is non-negative, otherwise the output is 0. And here is the function plot for this network. Suppose the input is minus 1.5. The input to the first ReLU neuron is positive, hence it is on, and the output is also 1.5. The inputs for the other two ReLU are negative, so they're off, and the outputs are zeros. Then we have the final output 0.25. Then let's check the pointwise repair specification. It says that if the network input is minus 1.5, the network output should be less than 0.1, and it is violated. Now we want to repair the network. Specifically, we will try to find new weights and biases that minimizes the behavior changes and satisfies that the symbolic output of the network is less than 0.1. However, solving phi and psi is difficult in general due to disjunctions and quadratic terms. So instead, we will try to find a linear formula filling that implies phi, then solve filling and psi in polynomial time using an LP solver. In order to do so, we will first eliminate disjunctions. Notice that if we constrain the symbolic input to the first ReLU to be non-negative, then we know that the symbolic output of the first ReLU is the same as input. Similarly, if we constrain the symbolic input to the other ReLU to be negative, then we know the corresponding outputs are zeros. Now we have a disjunction-free formula, and we want to eliminate quadratic terms. We notice that if we only make a single layer weights to be symbolic variables, and we make all the other layer weights to be concrete numbers, we can have a quadratic-free formula. Now here is the linear formula filling that implies phi. And now our pointwise repair becomes to solving this linear program. By solving it, we can get a repair network that satisfies the repair specification psi. Now I will give an overview of our polytope repair approach, using a very simple network and two polytope repair specifications, psi1 and psi2. Psi1 says that if the input is in the interval from minus 1.5 to minus 0.5, then the network output should be in between minus 0.1 to 0.1. Psi1 is satisfied. However, psi2 says that if the input is in the interval from 1.5 to 3, then the network output should be in between 0 to 0.4. However, side 2 is violated. Now let's take a closer look at it. For side 1, we notice that the two endpoints of it satisfy side 1, and the interval in between also satisfies side 1. But for side 2, for the two endpoints of it, they all satisfy side 2, but the interval in between does not. So what property distinguishes side 1 from side 2? We know that the interval for side 2 is in the same linear region of the network, but the interval for side 2 is not. Here is our observation. Given a polytope P, if P is in the same linear region of the network, and all vertices of P satisfy a linear constraint psi, then all points in P satisfy psi. And here comes our key insights. Constrain all vertices of P to have the same activation state implies that P is in the same linear region of the network, and apply pointwise repair on all the vertices of P implies that all vertices of P satisfy psi. Hence, we have that all points in P satisfy psi. Using this idea, we can get a repaired network that satisfies both psi 1 and psi 2. Now let's look at some results. We first evaluate pointwise repair for large ImageNet networks. Here we take a buggy VGG19 network and 50 misclassified fog-corrupted images from ImageNet C. Apron took around 2,000 seconds to repair it, where Pardon runs out of memory, and Ratio does not support such large networks. We also measured the test accuracy. The buggy original network has a very good test accuracy, and the apron repair one only decreased slightly. We also measured the generalization accuracy, where the buggy original network has 0% accuracy, but the apron repair one has 23% accuracy. Then we evaluate polytope repair in high-dimensional input space. Here we take a buggy MNIST network and a polytope repair specification, where we take one misclassified fog image and its 6 rotations as the vertices of a polytope, and we take 5 of such polytopes. Apron took less than 1 minute to repair it, where both Pardon and Ratio timed out. Then we also measure the test accuracy. The buggy original has a very good test accuracy, while the apron repair one even increased slightly. We also measured the generalization accuracy by looking at other rotated fog images, where the original accuracy is 0%, and the apron repair one has around 61% accuracy. We then evaluate polytope repair for complex global aircraft control safety properties. Here we take a buggy ACAS network, and all the five safety properties, and apron took around 100 seconds to repair it. And there are more results in our paper, and Apron is overall the best approach. To conclude, in this talk, we presented Apron, that is architecture preserving and supports efficient polytope repair, and it scales to large networks and complex properties. Thanks, and I'm happy to take questions.
Hi, so I had a small question. So you mentioned that in order to get rid of quadratic forms, you concretize certain variables so it will become a linear form. To me, that feels like a pretty large restriction. So what I didn't know is, did you have cases where because you restricted certain variables, your tool was unable to find a repair solution where if you left it at a quadratic form there, it would have found a solution? And if you haven't, do you think there ever will be a case like that?
Do you mean like where there ever be a case where our approach cannot find a repair? Like,
oh, yes, essentially, yes.
So our approach runs in polynomial time in the network size and the number of verses. So for example, if your input polytope has too many verses, then maybe it will not work. But in our case, like in our experiment, like for those pointwise repair, like for ImageNet networks, like they kind of always works, or like you always can find repairs, and that might because those large networks, they have many kind of redundancy, so it's kind of possible or very likely to be able to find a repair. Like there exists a solution.
I had a second question. So regarding the accuracy of the repair network, to me, it seemed like the resulting accuracy was still a little lower than what I would have ideally expected from a repair network. So is there a reason that, say, the repair accuracy does not come to the accuracy of the rest of the test set? For example, I think the first one, the test set had an accuracy of 70%, but the repair network on the bad examples only had 23%.
You mean here? Let me check. Let me go back. So do you mean that why the test accuracy?
Yes.
So here, where repair on some fork corrupted images, and there are like some new knowledges to the network. Like, so they are not trained with those images, so they had very bad accuracy on those fork images. But after our repair, like our repair is able to generalize to those new knowledges, so we have a much higher accuracy. Right?
So I guess my point is, what do you think we can do to increase it even more than, like, say, 23%? Because 23%.
Sorry, sorry, I cannot hear you clearly. So could you?
So I guess one of my questions is, so if I remember on the original, for at least for this network, on the original set that was not foggy, the accuracy was like something 70%. So do you think that it will be possible for this network to reach an accuracy of 70% on the foggy data set as well, or is that too much
maybe
to ask?
that's possible. Yes, maybe that's possible. So I'm not sure if that's possible to reach that kind of a high accuracy, but definitely, like, by doing this kind of repair, it's possible to reach a higher accuracy on those new knowledges. Yes, I think so, yes.
Okay, thank you.
Yeah, thanks.
We have some time. Does anyone else have any questions? All right, if not, let's thank the speaker again. You have a question? Okay.
Thanks.
Thank you for your presentation. So I have a question regarding the generalizability of your approach. So is your approach generalizable in terms of different kinds of neural network architecture, like CNN, RNN, and other architecture? And also in terms of different activation function. You showed for ReLU what about 10H and other in the model?
Yes, our approach supports most of the popular architectures, like convolutional layers, and yeah, I can show you slides, and like ResNet, and like those maybe batch nominators, like yeah, all of those kind of architectures. Yes. Yeah.
Okay. Thank you.
Yeah. Thanks.
Any late questions? All right. Let's thank the speaker again. Why not?